Welcome back to DR Electronics. In today's video, I'm going to be covering some of the mistakes I made with the breadboard adjustable power supply, particularly with the PTC resettable fuse along with the inductor in terms of its current rating and saturation current rating. And I'll also be taking this board and putting it under a resistive load that I made with some resistors in parallel on a perf board. So if you haven't watched the first two parts of this circuit and the PCB layout, I strongly advise you watch that first, as it will give you a lot more context in terms of what I'm using this board for and how I chose certain components and laid out the overall PCB. So we're first going to go over the PTC fuse, we'll cover the inductor, and then I'll show a demonstration of the board under different loads. The first mistake I made was with the PTC fuse in terms of its hold current and trip rating. So initially I had selected a fuse with a hold current of 750 milliamps and a trip current of 1.5 amps. I was trying to test this circuit given a 15 volt output with a 100 ohm resistor. This would result in 150 milliamps of current. However, as soon as I connected the resistor to the circuit, I noticed a high-pitched ringing noise and a significant voltage drop. At first I thought it was my inductor, given that maybe the frequency of it wasn't high enough, it was going into self-resonance. But I double-checked the frequency characteristics page, and looking at the 10 microhenry inductance line, we could see that at 1.2 megahertz there is no effect on it. So then what I decided to do was to measure the voltage across the fuse. Since I considered it was in line, it was directly in series with V-bus and V-in, maybe there's some sort of voltage drop occurring. And sure enough, there was. There was a 0.7 voltage drop across it. So basically what I failed to do was to consider the switching current of the inductor under the 5 volt to 15 volt output condition. So this hold current does not consider that, and because of it, the fuse essentially fails to regulate the system, thus causing a voltage drop. So I really should have selected a fuse with a hold current of about 1.5 amps and a trip current of 2 amps or maybe even 2.2 amps. So that was my first mistake. The next mistake that happened with this board was with the inductor. So the inductor that I originally used for this board has a current rating of 1.4 amps and a saturation rating of 1.6 amps. Now in the first part of this project, the first video, I showed a spreadsheet with different columns going over the calculations that were based off of TI's basic calculations of a boost converter's power stage. I've mentioned this PDF multiple times as I've used it in a lot of different boost converters that I've designed for circuit boards over the years. However, the mistake that I made was not calculating the maximum switching current of the inductor. This maximum switching current does not represent the current that is being put on the given load, but rather the current of the switching node for the inductor. So I forgot to account for that, and in the video I forgot to show how I actually chose my inductance value. So we'll first start with the duty cycle. Given that we have a 5 volt V-in and a 15 volt output, we can assume roughly an 85% efficiency, though it might be a little bit lower given the fact that this IC is typically a clone of other popular ICs that are used in electronics. We have a duty cycle of about 71% under this given condition. Now the switching current of the inductor can be calculated given the minimum input voltage, the duty cycle, and the switching frequency, along with the inductance. This gives us a result of about 0.3 amps or 300 milliamps. The maximum output current can be determined by the minimum switching current limit that is internal to the boost converter. This was found in the datasheet as 4 amps, and we already calculated the switching current previously here. So this result is basically based on these past two calculations and using the formula here. All of these formulas were ripped straight from the PDF. So again, I will link that PDF in the description, but I've referenced this many times before. This gives us a result of about 1.10 amps. Here is where I messed up. The maximum switching current of the inductor is 3.67 amps if we have an output current of 1 amp. With our change in the inductance currents, or current ripple rather, of about 0.3 amps and a duty cycle of 72%, this results in 3.67 amps. Now, I did make a perf board with 4 resistors, 4 100 ohm 5 watt resistors in parallel with each other. Given 15 volts, this would result in about 600 milliamps of current. Even then, we would still have a maximum switching current of 2.2 amps. So, given the inductor I selected, this is not high enough. And when I tried to plug in that load into my circuit with 15 volts, I noticed a little bit of smoke coming out and the inductor was getting extremely hot. So I quickly unplugged it, and given the current setup that I have with the inductor, I could do about 10 volts with 400 milliamps of current before it starts getting hot. I can push it further than that, but the inductor gets very hot, and that's because of the fact that it's not fully rated for the maximum switching current that the inductor experiences, given the drastic voltage difference between the input and output voltage. So while the current ripple of the inductor is fairly low or standard for a boost converter, the maximum switching current is high because of this. And the lower the difference between the input and output voltage, the better off your switching maximum will be, and the lower the inductor current rating needs to be for it. So basically, I wanted to kind of fix the issues that I had with my initial calculations. Thankfully, my inductance was correct. I calculated a value of about 9.3 microhenries. 10 microhenries is fine. We don't need it to be super specific, given the fact that this is not being made for mass production. I just want to use this for basic prototyping and small little breadboard circuits. And I also included a little section here just basically using Ohm's law, going through a load calculation, so that whatever the current is, you basically multiply it by 4. So it's this divided by this times 4. So that's where we get the 600 milliamps, because resistors in parallel, the current flowing through them will be different, but because we're using the exact same resistance value, the current's going to be more or less the same. So now what I'll do is I will show you the circuit under test. Okay, so here's the setup. I have the breadboard adjustable supply hooked up to a Raspberry Pi, which can output 5 volts and up to 3 amps. We have the left rail here set to 3.3 volts and the right rail set to 10 volts. Both of them share the same ground, so putting this second probe on the ground rail here doesn't make too much of a difference. Initially, I wanted to show the power supply transient response of this board, though I was a bit unsuccessful in capturing the waveform with this. My idea was to move the switch into a position where this extra resistance here, these 200 ohm 5 watt resistors, get connected to the full circuit, thus increasing the load. Wasn't really able to show that here on the oscilloscope, so what we're going to do first is we're going to check the peak-to-peak ripple voltage of the boost converter's output with no load. So right now I have the first channel set to AC coupling with the bandwidth limit to 20 megahertz, and the probe is on 1 times attenuation. So basically all I'm going to do here is just probe the line, and we could see we have a ripple of about 184 volts peak to peak. So it's fairly high, and that's why you see this kind of noisy sawtooth wave here. Now, if I was measuring this directly on the board with a ground spring, that would give us a better indication of what's going on here. We also have to consider the fact that breadboards induce their own resistance, capacitance, and inductance, along with boost converters are noisy circuits. You know, the switching node here, that's why you don't want any traces running underneath. You don't want any other additional circuitry close to this. If I were to revise this board, I'd actually probably move this 5-volt trace and put it underneath the LDO, or just move it further away from the inductor, because you want to keep this section of the circuit as clean as you can. And you know, it's kind of hard to do that given the fact that we're using a breadboard setup, but this is what the peak to peak looks like with no load. Now what we're going to do is we're going to connect this perf board that I have here. So I haven't shown this yet, but it's super simple. It's literally just 4 resistors in parallel that I soldered together. So I bent the leads and then I just made a solder bridge across them, and towards the input I just put a red wire for the positive and a black for the negative. So we're just gonna connect this here. And now what we're gonna do is we're gonna measure the peak to peak. So if we look here, the peak to peak is actually a little bit higher. So I'm gonna adjust with the settings to give you a more accurate representation. Okay, so here's the peak to peak voltage given the 400 milliamp load that we have connected at the output. It's not the best waveform and the measurements are kind of all over the place. I tried adjusting my trigger to get a better scope view of this, but this is really just the best that I could do for it. So now what I'm going to do is I'm going to show you what the switching node looks like without a load and what it looks like with a load. So first, I'm just going to confirm that we're getting 10 volts on the rail. As we can see here, we have an RMS voltage of 10 volts. And now what I'm going to do is I'm going to take my channel 1 probe and I'm going to directly probe it against the right side of the inductor here. And we can see without a load, we have a frequency of 1.27 megahertz with an RMS voltage of about 6.27 volts. Now what I'm going to do is I'm going to take this parallel load perf board and plug it into my rail, and then we're going to re-measure the switching node. And here we can see we still have the same frequency of 1.21 megahertz and a little bit of distortion at the top and bottom of the waveform. So I'm not pushing this converter to the absolute maximum capabilities, nor am I giving it a high enough load in which we could see a better resulting output. This is only about 400 milliamps of current, and I'm going to show this in just a second by making a break in the circuit, and I'll measure it across the breadboard. But essentially, I just wanted to give a better picture of how the switching node behaves with a load and without a load. So here is the ripple voltage of the 10 volt output given a parallel load with 4 resistors. As we can see here, that we have a peak to peak voltage of 160 millivolts, and there is quite a bit of noise and distortion, especially here, considering this is much higher than the lines here with the ripple voltage. Given our parameters and what we designed and the fact that we're using a boost converter on a breadboard, which the breadboard has its own resistance, capacitance, and inductance, I don't think it's too bad, but I would definitely make some changes. The inductor, I would use an inductance of a similar value, but with a current rating of at least 2 amps and a saturation rating of 2.2 amps. That would still fail our given condition of using 15 volts at 1 amp when we went over the calculations with the maximum switching current of the inductor. But at the very least, we would still be able to push this board further than the limitations that we currently have. Also, I think I would probably add some additional output capacitance and the layout in terms of the potentiometer RV1 and R4. The feedback node is fairly large, so I would add a capacitor in parallel with RV1 in order to reduce any sort of noise that is coming from this component. I would move the trace that is seen here away from the inductor, as the inductor is the noisiest component on this board. And in the future, I will try and avoid using boost converters on breadboards, as they are not the most clean or sufficient way of generating voltages. I know that I was trying to initially make this board so I don't have to pull out my power supply every time I want higher than 5 volts, but I think that this board is definitely limited in terms of what I could use it for. It'll still suffice for basic prototyping and simple transistor circuits and maybe even some op-amp stuff, but if I want a clean supply rail, this may not be the best board to use. But nevertheless, it was definitely a good learning experience, and I even tried to reduce the ripple here by adding a 470 microfarad electrolytic capacitor along with some film capacitors. I think these are rated at 0.047 microfarads. Didn't really help too much. It made somewhat of a difference, but there's still a decent amount of ripple there, as we see on the scope. But nevertheless, this was definitely a good project and a good learning experience, especially with the PTC resettable fuse, which now currently I just have a 0 ohm resistor, and the board is no longer making that annoying screeching noise, nor is the voltage dropping significantly. As always, thank you all so much for watching. I have content involving digital potentiometers, STM32 firmware setup, PCB manufacturing with JLC PCB, old projects, along with the first 2 parts of the breadboard adjustable power supply. More content will be coming soon, as the next video I will be releasing will involve the dual polarity power supply. So once again, thank you all and have a great day.